All right. So Hussein Fawzi was a staff research scientist at DeepMind, ex-Google DeepMind, and now he's the co-founder and the CEO of Stealth Startup. Until recently, he was awarded the MIT Innovators Under 35 Awards in 2023 for his work on discovering new algorithms with machine learning. He has worked for AI for Science, with particular interest in using machine learning to unlock new results in computer science and algorithms. He recently published 2 papers in Nature, because 1 paper isn't enough, and where he used machine learning and large language models to discover a new algorithm for fundamental computational tasks and the new mathematical results. He has published more than 30 papers in major conferences and journals, and he's a really nice guy who also ran the NESMA machine learning school in 2016-17. Very similar, the inspiration behind Mina as well, MenaML. So yeah, leave it to him to take you on a really nice journey.
Thank you, Sami, for the great introduction and for the great organization of this school. It's always a great pleasure to attend those and to see the excitement behind machine learning in the region. So today I'd like to tell you a little bit about something that is perhaps a bit different from the rest of the talks, which is how can we use essentially foundation models in order to make new discoveries, to discover new things essentially, right? So if you think of foundation models as a compression of the whole human knowledge, right, because these things are trained on the whole of internet, how can we use those in order to go beyond the existing knowledge and discover new things? And I'm going to focus specifically on the area of computer science and algorithms, right? So essentially focusing on the discovery of new algorithms. Now, before going into that, I'd like to tell you a little bit about why there is a pressing need to discover new algorithms. So let me check if this works. Doesn't seem to be working. Okay, great. So if you look at the kind of decision-making problems that we have nowadays, they are gaining in significantly and even exponentially in complexity. Not only in terms of scale, but also in terms of the dynamic nature, right? So we need to really solve decision-making problems in real time. So take, for example, data centers, right? So data centers are doubling in capacity every 4 years. In 2026, we will have these data centers consuming more energy than Japan, right? And that's, I think, even an underestimate. So with the ever-increasing scale of those data centers comes great challenges. In particular, how do we cool those data centers? How do we control those data centers? How do we schedule jobs on those data centers? So these are really unprecedented problems in terms of challenge, and in terms of scale, and in terms of dynamic behavior that we really need to address if we want to make those essentially scale with the current capabilities that we have. It's not only limited to data centers. If you look, for example, at the energy space, right? So we do have now in the grid more and more renewable energy. So with the renewable energy, that means that this is very much unpredictable generation, right? So we essentially need to solve these real-time optimization problems that are fundamentally very difficult and that scale exponentially. So in particular, for example, if you have a grid of generators, how do you essentially determine how to generate or how much to generate from each one of those, right? And how much do you store in the batteries, right? So these are all fundamental decision-making problems that you need to solve in real time and that are becoming very challenging with the increasing amount of renewables. Now, a third example, which is a bit different from those, but I think is becoming very prominent, is that of scientific discovery, right? So with the advent of more and more robotic arms, essentially, that do the experiments for us, so essentially robot scientists, we essentially automated this process of experimentation, and the question then becomes, what experiments do I do, right, in order to arrive to the fastest possible to a certain new discovery. Say, for example, the discovery of a new material with certain properties, right? So the question of which hypothesis to test for each of those experiments is really fundamental, and that's really a fundamental decision-making problem. So my argument, or my take on this, is that in order to tackle those problems, we really need to develop new algorithms that go beyond the existing ones, right? And we really need to kind of like go beyond this algorithmic bottleneck that we are currently at. Because if you actually look at the current ways these decision-making problems are solved, they are either using like decades-old heuristics, right? So essentially static algorithms that don't really adapt to the real-world nature of these problems, or like the real-time nature of these problems. They are essentially like a one-size-fit-all algorithm, right? That have been invented by very smart people, but that are essentially like one-size-fit-all. Now, the other approach, of course, is using machine learning methods, right? So there are machine learning-based approaches in order to tackle those fundamental algorithmic questions. But the problem with this is that they really lack trustworthiness. They don't work well with hard constraints. They are expensive to deploy, and so on, right? So take for example the data center space, right? So you don't want a neural network to be controlling the cooling of your data center, right? What if something like out of distribution happens? How will my neural network policy behave to this out of distribution sample, right? So this is really fundamental, I think, and really a hurdle towards implementing those data-driven approaches in especially safety-critical environments such as data centers. So what I'd like to essentially talk about today is a new paradigm, is a new way essentially to discover new algorithms that are essentially adaptive and that evolve accordingly to the data, but that also have this trustworthiness in them and the verifiability that we love in essentially like non-machine learning based approaches. So perhaps to summarize, like the mission I have been working on for the past few years has really been the following: to discover new, verifiably correct and efficient algorithms for impactful problems. Right, so there is a few keywords here. New, meaning that we really want to go beyond existing algorithms, right? So we believe that there is just so much headroom we can have by discovering those new algorithms. Verifiably correct is super important. When we deploy this, as I said, in safety-critical environments, we want this to be correct, interpretable, so humans can read it, right? And we want to do this for impactful problems, right? What we call at DeepMind, for example, root node problems, in the sense that if we tackle those, if we're able to solve those problems, then this can have immediate implications on other fundamental problems. So the first, perhaps the first work in this area was essentially like doubling down on a fundamental problem, one of these root node problems as I was talking about, which is that of matrix multiplication, right? So I'm quite sure that many of you are aware of what matrix multiplication is. But essentially, it's an operation that is present essentially in all computational tasks, from like simulation to neural network training to like solving linear systems. You name it. You have essentially matrix multiplication. So then the question is, what if we're able to accelerate matrix multiplication with AI, right? What if we are able to discover new algorithms to do matrix multiplication that are faster than the algorithms that we have been using so far? Then if we're able to do this, then this will have huge implications on all these fundamental problems that we tackle every day. And so what we did here is essentially to use reinforcement learning, and I think there was a course on that yesterday, AlphaZero-based approaches in order to discover verifiably correct algorithms that do matrix multiplication faster than what's existing. Okay? Great. So maybe just to kind of zoom in a little bit on that. As I said, I'm sure like everyone here is familiar with matrix multiplication, but in case you kind of like you haven't seen it before, so this is essentially the operation of matrix multiplication, right? So you have here like the operation of 2 by 2 matrix multiplication. So that involves essentially like 8 scalar multiplications here, and then you distribute them in this way, right? So that's the standard algorithm that we were all taught in high school or university. Now, what happened is that in 1969, a German mathematician called Volker Strassen was actually trying to prove that this is the best approach to do matrix multiplication, but then he came up with a very weird-looking algorithm, right? So he came up with an algorithm that looks like this, right? And the idea here is that he combined entries of the first matrix together, entries of the second matrix together in this way, in this weird way, and then distribute them in this even more weird way, right? Now, if you actually do the calculation, you will see that this is a correct algorithm to do matrix multiplication, right? So this is like the algorithm on the right and the algorithm on the left here are exactly equivalent, right? You can do the verification yourself. You can do it on a piece of paper and actually verify that this is exactly the same. Now, coming up with this algorithm is very different, right? So, I mean, if I had to give you a blank sheet of paper and tell you, can you come up with a better algorithm than the one on the left, right? Then that would be much harder, and it's really hard to imagine what was his intuition when he said, okay, like let's add these two entries together and so on. Now, one important point of like why the algorithm on the right here is better than the one on the left is that the one on the right involves 7 scalar multiplications as opposed to 8, right? So the traditional way of doing matrix multiplication involves 8 for 2 by 2 matrices. Here we have 7, right? And the important point here is that if you apply this algorithm recursively, so let's say now that you have an n by n matrix multiplication operation, then you can decompose this n by n matrix into blocks of n over 2 times n over 2, so 4 blocks, and essentially apply this algorithm, right? Recursively, right? So you do this for n by n, and then you get matrix multiplication operations of size n over 2 times n over 2. You do again this algorithm and so on, so you can apply this algorithm recursively, and then you get a complexity of n to the power log base 2 of 7, which is n to the power 2.81, right? So compare this to the traditional way of doing matrix multiplication, which takes n cube, right? So this was a huge surprise to the mathematical and algorithmic community that you can do better than n cube. Why is that? Because of the fundamental nature of matrix multiplication. Now, when I looked at this algorithm for the first time, I was saying, okay, like this, like machines should be much better at humans, which should be much better than humans to develop such algorithms, right? Because at the end of the day, I mean, how do you get the intuition here that you need to add those entries together and distribute them in this weird way? As I said, verification is easy, but getting to this algorithm is really hard. Okay, so what if we have a machine that's able to essentially propose those algorithms, right? And so that's exactly what we did. Now, if you actually convert this problem into a combinatorial problem and develop, you know, like and try to develop an approach for that, so you could compare this the difficulty of this problem with, for example, a game like Go, right? And you'd soon realize that the complexity of this problem is way more than that of Go. So for example, for 2 by 2 matrix multiplication, the action space, so the action space meaning the number of possibilities you have at each step is much larger than that of Go. It's actually very hard to enumerate those. So you need to really design new approaches to do reinforcement learning when you cannot enumerate your actions. So for Go, the action space just corresponds to the size of the board. So it's just 19 times 19, right? But here, you just have so many possibilities. So here, for example, you can add you can add, you can subtract, you can do whatever you want, right? Which entries do you select, and so on. So you can see that the complexity of this problem is just humongous. Now, in terms of how did you actually go about solving this problem, so this was a multi-year effort just to develop, just to find those new algorithms to do matrix multiplication, right? So this involved several steps. The first step was to translate this problem into a Markov decision process, essentially, to use reinforcement learning on, right? So this involved essentially taking this problem and then convert it into an approach. I won't go into more details. You can look at the paper if you're more interested. But essentially, you can have a board, like the board, the corresponding object to the board in Go is a 3D tensor, right? And at each step, you need to find a rank 1 tensor. You have a reward at each step, and then you have a final reward corresponding to how well you did, right? So that's essentially like the idea behind the formalization of this. Once you have this, then you need to develop an agent for that. So we built on top of AlphaZero. As I said, there was a huge number of difficulties to actually develop this agent. Like the action space was large. There was really no training data. So unlike Go, for example, where you have lots of games online, you cannot really rely on existing data. And then it's one of those problems where you just have one test point that you care about, right? So this is quite common in discovery problems where you really have essentially one particular operation that you care about. So say, for example, in this case, it corresponds to the tensor of matrix multiplication, right? So I care about just decomposing this one tensor, and if I decompose this one tensor, then I have an algorithm to do matrix multiplication. That's what I care about, that's it. And if you think about mathematics, that's the same. Like I care about this proving this one theorem, and that's it, right? So that's usually the case in those discovery problems where I'm tackling an unknown instance, essentially. So in this case, it's matrix multiplication, but in mathematics, it can be a theorem for which you don't know the proof, right? So these were some of the difficulties. Then you essentially deploy this and run these RL experiments, and then you essentially, after a lot of trial and error and so on, then you get those algorithms that outperform Strassen's algorithm in this case for 4x4 matrix multiplication for the first time in like 50 years. But what I want to highlight here is that there was a lot of challenges along the way, right? Just for this problem of matrix multiplication. So as I said, like this was a multi-year effort to develop an agent for a single problem. So this was really problematic. So what if I want to apply this to another problem? So say, for example, a problem in the data center space, as I mentioned, do I have to go again through this multi-year effort? That would be a problem. It requires a large amount of resources, right? So, I mean, RL is expensive. And the last one here is that many problems do not lend themselves to this nice combinatorial structure that we just saw here, right? So we were lucky that we were able to convert this problem into a nice combinatorial problem, but then many problems don't have this. So what I'd like to tell you here in the rest of the talk is essentially another approach where we leverage foundation models to discover new algorithms that go beyond state of the art. Right? So it would be just amazing if we had a box that we would ask it, okay, like discover new algorithms to do matrix multiplication, for example, that are better than existing ones, and then it would just spit out an algorithm that goes beyond what we have, right? So that would be just fun, really great. And we wouldn't need, like to adapt it or to have this multi-year effort to develop this agent for every single problem. Now, we can try this, right? We can take ChatGPT, for example, and ask it, okay? Ask it the same question as what we had before. Can you discover a new algorithm that outperforms Strassen's algorithm for 4x4 matrix multiplication, which is essentially what was found here using the reinforcement learning agent. Now, we did this experiment. We asked it, find a better algorithm to multiply matrices, for example. Now, what we got is unfortunately something that doesn't make any sense. So you get an algorithm that, or you don't get, like a meaningful answer in any way. So you get a hallucination essentially, and that's most of the time you get this when you deal with those problems that are super specific and quite advanced. Now, in other times, you get existing algorithms. So you get, like what's known already, which is not really what we care about. We really care about like discovering these new algorithms. Now, does that mean that those foundation models are useless in order to achieve our goal? No, not really. It's actually very useful, as we'll see, but we don't just have to use them in this very simple way of just prompting them, and that's it, right? We have to do something on top of that in order to get to these new algorithms that I was talking about. By the way, is there a time or something I can keep track of? Take my phone. Okay. Okay, so what we did in this following project called Fun Search for search in the function space was essentially to combine the creativity of large language models with an evaluator that guardrails it against these hallucinations. Okay, so we combine these two things together in order to produce those new algorithms. Now, in computer science and mathematics, these domains are super interesting because many problems have this property that verification is easy, but solving is hard, right? So if you give me a candidate solution for a hard problem like the independent set, for example, it's easy for me to check that the solution you just gave me is correct and even score it, tell you how good it is. But coming up with a solution myself is really hard, as we saw a little bit before, right? So, like in the algorithm that we saw before, verifying that this algorithm is correct was easy, but coming up with it is really hard, right? This is a common property across many problems. So maybe I should say what the independent set problem is, but essentially the independent set problem, the maximum independent set problem is that you have a graph and you want to determine what is the largest set of nodes in this graph such that there is no two nodes that are connected. Okay, so this is a very fundamental problem in computer science, and it's one of those, as I said, where verification is easy but solving is hard. The traveling salesman problem is also another instance of this, right? If you give me a candidate tour in your graph, then it's easy for me to check if this is a real tour or no, and even score it. But coming up with a tour is really hard, or coming up with a good tour is really hard. So essentially what we're doing here is that we assume that we have one of those problems, right, that are super interesting, like that are already like a big class of problems. So we do have access to an evaluator. We do have access to a way to evaluate how good a solution is. And then we essentially try to determine or try to solve this problem using Fun Search, okay? So we have one way, but we want to go to the other way with Fun Search, okay? Is that clear? Yeah, okay. So, as I said, Fun Search stands for search in the function space, right? So let's assume for now that the function space, or the, by function here, I really mean Python function, right? So it's essentially like a piece of code, right? So what we really want to do here is program search or function search, right? To try to find those functions that are high scoring in terms of my evaluation criteria. So let's assume for now that the space of functions is like nice and continuous and 2D, right? So each point here corresponds to one function, right? And the color here represents how good this function scores in terms of my evaluate function. Okay, so what I want to do essentially is to go from, or like to start from a very poorly scoring function, so V0 here, to one that scores quite high, right? So I want to essentially solve this optimization problem in the space of functions, right? Now, of course, the real picture is very different, right? It's much more discrete problem and so on. But just for kind of like presentation, this is, I think, is quite useful. So what you can do is, okay, you're starting from this solve function. You can sample from an LLM. So you can say, okay, like, can you please improve over this solve v0 function, right? Now, 90% of the time, you'll get something that doesn't make any sense or doesn't compile or so on. But sometimes you will get a slight improvement. But in no way you'll be able to get essentially to this red area here, right? That you really care about, that scores quite high. So this is the area where you have, for example, a small tour for your traveling salesman problem or a large independent set for the independent set problem and so on, okay? Now, as I said, like you sample a lot, you will never be able to reach this. However, if you essentially like iterate this process, try to essentially sample from an LLM and then chain the mutations together, then you might be able essentially to arrive to this region on the left. Okay. Now the question is, how do you like? Which one do you build on, right? So what are the good samples that you need to build on, right? So this is essentially like the whole idea behind font search is essentially to try to build an evolutionary algorithm on top of LLMs, where LLMs give you the mutations. Okay, so you have the LLMs that try to improve, right? So many mutations are just garbage, but some of them are good. And you essentially try to build an evolutionary algorithm on top in order to reach those high-scoring places in your function space. Okay? So let's try to be a bit more concrete. How does this look like? So what you take in as input is essentially a specification, which is a problem specification. So as I said, we need an evaluate function, and we need a solve v0. We need a version 0, right? Now what you're going to do is that you initialize your population, or what we call your programs database, with this v0 function, right? And then you're going to sample from this programs database or from this population a few of those, right? You're going to put them in the prompt and then ask the LLM, can you improve over those? As simple as that, really. So no gradients, right? So we have a pre-trained LLM, right? So we use a pre-trained LLM that is trained on a lot on code, but no gradient, essentially no training of the LLM, right? So we just keep the weights fixed. We ask the LLM, can you improve over that? The LLM gives you some candidates. As I said, like you go through the evaluate function. Now, many of those are not going to be correct, are not going to compile, but some of them are, right? And if the ones that compiles, you take them, you add them back to the programs database, and then you iterate and iterate and iterate, right? So this is the high-level idea. Then what you'll be getting at the end here is a novel program, a program that goes beyond existing results. Now, the whole intelligence here, or the whole difficulty, is how do you select those? How do you select essentially those two programs that are dashed here, right? How do I select the programs that are the most promising to build on, right? Now, I won't go into the full details, but let me just give you one element that was quite important when we designed this sampling algorithm. So one important point here is that you want to have diversity in your population, right? You don't want you don't want to essentially converge to just a single program or variants of a single program, right? So you want to have as much diversity as possible. And this is really fundamental in evolutionary algorithms. So what we did here is an approach based on islands, where you instead of just evolving a single population, you essentially evolve separately different islands. So essentially you're running many small experiments as opposed to one big experiment, right? So to avoid this local minima behavior. So you evolve them separately, and then after some time you say, okay, I want to actually kill the ones, or like remove the ones that are the least promising in some metric, and essentially migrate the ones that are the islands that are good to those ones that we just killed. Okay, or like migrate the best function here in one of those islands, right? So the best function in this island, I think I have a cursor. Anyway, the best function in one of those islands, I want to migrate it to this newly created island. Okay, and then evolve it again, start again the evolution. Right, so this allowed us essentially to have much more diversity in the population, and therefore essentially have a better exploration of this, remember this 2D space that I was talking about. Okay, so now let me tell you a little bit about applying this to some fundamental problems. The first one I would like to apply it on is this maximum independent set problem, right? So remember that the maximum independent set problem is the following. You have a graph, and then you want to find the largest set of nodes in this graph such that no two nodes are connected, okay? So for example, the largest independent set in a complete graph is 1, right? Okay, so we want to apply it to this hard problem. Now, we don't just want to apply it to random graphs. We want to apply it to graphs that have particular significance, right? So we took a graph that is particularly significant from a mathematical standpoint. So it's called the CAP-set graph. And according to one of the most famous mathematicians, this is like determining the largest independent set in these graphs is one of his favorite open questions. So it's something that really is fundamental from a mathematical point of view. And so we applied this approach to try to find those large independent sets in the graph. And what you notice here is that, so we applied it for different dimensions, right? So this problem is parameterized by different dimensions. The bigger the dimension n, the larger the graph, essentially. And what you're getting here is for each of those, you're getting a function that finds those large independent sets. So for n is equal to 2, for example, you're getting a construction, the font search construction, that is as good as the previous construction, right? But these are relatively small graphs. Now, when you go to larger and larger graphs, still the functions you're getting are matching state of the art. But then at some point, when this graphs essentially scale a lot, then it really goes beyond human intuition that are essentially, are the ones that essentially these previous constructions were determined using human intuition. So when you scale a lot, then you really go beyond what humans can think of. And this is where essentially you're getting these better constructions, right? These constructions that go beyond state of the art. So if you continue, then you essentially get a better asymptotic result also. And that's essentially, I think, that was really fundamental in essentially convincing us that that this is a really good approach in order to search in the space of to search essentially for these new mathematical results. Now, beyond the quantitative results here, I think there is really a fundamental point here that I'd like to stress on. Now, previous search techniques were doing the search essentially in the space of nodes, right? So you have a graph, you try to find the largest independent set in this graph by essentially, trying to find, trying a search procedure on the nodes of the graph. Now, what we are doing is fundamentally different. We are searching in the space of functions. In the space of functions, such that when we execute this code, we get this large independent set. So that's two very separate things, right? So in the left here, you have a search in the space of nodes. On the right, you have a search in the space of function, that when you execute this function, you get the largest independent set. Now, in terms of interpretability and mathematical explainability and so on, the right, I don't think I have to convince you that it's much, much better. Because if you look on the left here, which is this large independent set, you barely see anything. And you're not the only one. Mathematicians also barely see anything. Like you give this to a mathematician, he'll tell you, I don't know how to do with this. But you give them the function on the right here, and they understand how this large independent set on the left here was created. So they, like you can think of this, that the left is the what, the right is the how, right? So you can, so yeah, I mean, from an explainability point of view, it's pretty clear. Okay. Now, this, as far as we know, this was the first discovery made using LLMs. But as I said, this is just a new computational paradigm because it tells you also how, like it gives you understanding rather than just facts, right? And we worked with a mathematician, Jordan Ellenberg, and he was essentially able to learn things from these kind of programs. Okay, now, to be honest, I spent a long time trying to understand why this thing works, why this approach works at all, right? Why is it better to search in the function space than it is to search in the space of, you know, like in the space that is most logical, which is the space of nodes in the thing on the left here. While I don't have a full answer to this, I think there is an argument to be made here. So the argument goes as follows. Most problems we care about are structured, do have some degree of structure. And because most problems are structured, the ones that we care about are structured, the solutions to them tend to have what we call a small Kolmogorov complexity. So what's a Kolmogorov complexity? So Kolmogorov complexity is the length of the shortest computer programs that outputs a certain string, right? So the Kolmogorov complexity of this AB string, right, is much smaller than the Kolmogorov complexity of a random string. Why is that? Because if there is a very short program that essentially outputs the string AB, but if you had to actually write a program to produce a random string, then that would be much longer. Okay? So the problems that have structure, or like the strings that have structure, they have a smaller Kolmogorov complexity than the ones that don't have any structure. Similarly, the image on the right here is a fractal, right? So the fractal has a nice formula to it. If you had a random image, then that has a large Kolmogorov complexity. But an image on the right here that is a fractal has a small Kolmogorov complexity. Now, why am I saying this? Well, I'm saying this because essentially what we do with fun search is a search in the function space with an implicit prior that we are encouraging solutions with concise functional description. And so by searching in the program space, we are encouraging solutions, right, that have a small Kolmogorov complexity. While when you do the search in the space of nodes, you don't just encourage anything. Like a random solution and a structured solution has exactly the same probability to sample from. Is this a bit clear? Yeah? Okay, I mean, maybe like ask me if you have questions at the end. Yeah, sure. If you have questions on that.
Kolmogorov complexity is small. So if I got you right, you're basically enforcing that through the prompt, right?
So there are an implicit way and an explicit way that we're doing. The implicit way is that since you start from a short program anyways, then it evolves, when you have this evolution process, it evolves to a program that is also, you know, like not like 200 lines of code, right?
It can go anywhere, right?
No, it's not. I mean, LLMs usually, I mean, when you sample from an LLM, right, it will not like add you 300 lines of code or 400 lines of code. It will, you know, like do a small mutation. It will add perhaps like a few lines of code, but it will not add a crazy number of characters, right, to your program. So there is an implicit way of doing that, but we are doing it also explicitly in the sense that we are, like the score has some built-in formula to encourage concise programs. Okay.
But I can add something to a program that's not really adding to the functionality too. So it will compile, but it will still not be informative.
Yeah, but I mean, take it as a multi-objective thing. So if you have two programs that have the same score, then we will keep the one that is shorter, right? So it's a secondary objective.
Yeah, thank you.
I have a question about alpha tensor here.
Yeah.
So So you mentioned that the action space is very large, like 10 to the power of 23.
Yeah.
And you guys use like Monte Carlo tree search to among all the possibilities. How do you balance the exploration versus the exploitation trade-off? Like, do you use some sort of heuristics for that?
Yeah, that's a great question. This was one of the challenges that we faced. So we used a version of MCTS called sampled MCTS, which is essentially like, because we cannot enumerate the whole action space, right? So we sample instead. But if you sample bad things, then nothing will happen, right? So that's why, especially at the beginning, we were generating some synthetic data, right? Some synthetic data in the sense that we were not exactly dealing with the matrix multiplication problem, but random versions of it, right? And for which we had the solution, right? So so this essentially biased it towards sampling the right actions and understanding really the problem of tensor decomposition, which is essentially what we're dealing with here. So it's a great question. It's very hard to actually find the right actions, especially at the beginning of training. That's why you need some essentially supervised training at the beginning, right? So, and we initialize it with that.
So how interpretable are these programs?
Yeah,
like,
I'm going to go through that now,
yeah.
okay? So I mean, from the math point of view, this was quite interpretable in the sense that, I mean, I didn't present exactly the mathematical, like problem, what is a cap set and so on, so probably it would be a bit hard to kind of like relate the two. But essentially, yeah, it's like there are some concepts here, like for example, counting the number of non-zeros, the reflections. It came up with this concept of reflections. That was super interesting, for example, for Jordan. When he looked at it, he never thought that reflections would be an interesting thing. So maybe I can go to the, yeah, I mean, the next problem I want to tackle is more, how do you do this? So the next use case I want to tackle is more, like practical. It's essentially the problem of bin packing, which is like present a bit everywhere also. Like if you have a container and you want to put items in a container to maximize the utilization of the containers or to minimize the number of containers, that's a bin packing problem. If you have a data center and you're sending jobs into a data center and you want to maximize the utilization of the data center, that's also a bin packing problem, right? So bin packing problems are a bit everywhere. And I mean, the formal problem goes as follows. You have a collection of bins, right? And a stream of incoming items, and you want to place each item in bins so as to minimize the total number of bins used. Okay, so these are examples on the left, and where you have like what, 6 bins, and you have incoming items, so it's an online problem, right? And you want to place those items so as to minimize the number of bins. And you can see the heuristic on the left here is using all the 6 bins, but the fun search approach here is able to pack those items using less bins. Now, this is a toy example, of course, and you can apply to more real data. And real data verify this claim that essentially you can use much less bins using this approach compared to existing heuristics. Now, as I said, like one of the nice things about this is that you're getting code, right? So you could try to solve bin packing using a neural network, but then the thing that solves your bin packing problem is a neural network, so it's not interpretive in any way. But on the right here, you have a heuristic that essentially tells you how do I score all my bins, right? And then I'm going to take the one that maximizes the score, and then I'm going to repeat and so on, right? So it tells you exactly what is it that I should be picking, and this is data specific, right? So if you deal with a bin packing problem for certain data and a bin packing problem for another data, then the programs you're going to get are different, right? So that's really fundamental, and this I think goes beyond the kind of like heuristics, like universal heuristics approach that we have been working with for a long time. It's also easier to deploy, to debug, so in the sense that you can edit it and so on, more understandable, predictable, scalable. For which kind of problems does this work well? It works well specifically for problems where you have an efficient evaluator, right? So you need to evaluate a lot, so you need to have this evaluator that runs fast, and for smooth scoring feedbacks, right? So if you have a problem where you have just a binary answer, then it's not going to work very well, because remember, we're doing essentially an optimization in the space of code, in the space of programs, right? So we need to do this hill climbing. We need to have some sort of like, not necessarily continuous, but some gradual scoring, okay? I didn't go in details about, you know, like all the elements that were needed in order to make this work, but I went through the diversity, so like the islands, but then there's other approaches like merging, skeleton, and so on. So merging is essentially the idea of sampling many programs versus just one program from your population. Skeleton is really important in the sense that you need to essentially make the LLM work, not give it essentially an empty sheet of paper, right? So say, for example, you're developing a greedy algorithm, right? So you give to the LLM the task of finding the priority function. The function which essentially tells you which element should I visit first, okay? For us, I mean, priority function is the most important thing in a greedy algorithm. But for an LLM to come up with a greedy structured algorithm and then find the priority function is much harder than just we, you know, like define the skeleton, which is a greedy structured algorithm, and then we let it, we ask it to essentially find the priority function. Okay, so it's important to kind of like tell the LLM, or like let the LLM do its thing where we don't know how to do it, right? In this case, for example, the priority function. So yeah, if you have like this is the paper published in Nature about fund search. Now after the paper was published, there was lots of follow-ups. In particular, one follow-up that is particularly interesting is from colleagues at DeepMind that use this approach essentially to solve combinatorial competitive programming problems. So essentially Google hash code problems. So these are problems obtained from the Google ecosystem. Like, for example, from Waymo, from YouTube, and so on. And so these are sort of real-world problems. Every year, Google was organizing competitions around this to try to find the best solution for these approaches. Now, if you apply fund search on these problems from very different fields, like, for example, self-riding rides, or delivery, or optimizing data centers, and so on, then what you're getting is consistently that fund search gets a score in the top 1 percentile, and in many cases outperforms the best human competitor, right? Human competitors were just trying to find those heuristics. This is essentially always much better than most competitors at finding those heuristics to solve those problems. So beyond that, and this is really my last slide here, I think what we're witnessing here is the birth of novel LLM-discovered algorithms to solve these fundamental and ever-scaling problems that I was talking about, like from data centers to batteries to logistics and so on. The nice thing about them is that you get interpretable, easily, or like verifiably correct and data-driven algorithms. So I'm really excited about this line of work, and really think that many of those algorithms that are being controlled, or like these problems that are being controlled currently by heuristics, will be transforming into like this LLM-based approach. So as I said, as Sami said, I recently left DeepMind to create a company still in stealth mode. We're well funded, so we're hiring currently. If you're interested in these topics that I talked about today, feel free to approach me. Thank you.
thank you for your talk. I have two questions. First, do you see any kind of problems where LLM cannot anymore improve upon, so the answer is saturated? Second question is, how do you convert binary unit tests into gradient, like you said it's important to have gradient scoring?
That's great questions, yeah. So saturation. Yeah, I mean, especially when you deal with problems like the CAPSET problem, for example, where you don't know what's the best answer, like in problems that are open. These are really hard because you're getting a saturation and you don't know if the saturation is coming from the method itself or from the fact that there is no concise piece of program to solve it, or from the fact that it's just a problem where you reached already the optimal. So it's a really hard thing to, to determine whether this saturation comes from where. Now, having like the empirical answer to this is that whenever we thought that we were saturating because there was no concise functional description to the solution of the problem, we were wrong. Right? So we were in this situation many times where we had this saturation, and then we improved the method, and then we were getting essentially like better results, right? So, but yeah, I think it's a great question, and I think it's. I mean, as I said, like the algorithms here, or like the evolutionary approach that we used here is very simple. So in order to if we increase the diversity of the population, if we improve the algorithm or the evolutionary algorithm itself, I think we will be able to do much better than what we have currently. But already with this relatively simple approach, you're able to get those results. So yeah, I think it's essentially, like there is a lot of work to do to improve on this kind of algorithms. Now, in terms of the unit tests, the way you would do it is that you have many different unit tests, and then you essentially score how many unit tests passed and how many unit tests failed. And that would give you a concrete score about like how good your current function is.
Thank you for the talk. I want to ask you about like what was the inspiration behind using an evolutionary approach rather than just using a reward-based model, like just giving a positive or negative reward?
So this is a bit of a different setting than reinforcement learning. If that's, I'm not sure I understand the question, but if that's the question, then the setting is slightly different here, in the sense that at each step, what you're getting is a program that runs and for which you can evaluate how good it is, right? So there is no value function needed. So I mean, evolutionary approaches are very popular in the case of black box optimization, and this is typically the case of a black box optimization, where a discrete black box optimization where we can evaluate at each step how good we are, but we don't have any gradients. So I think it's quite natural here.
Thank you. To what extent would you say that the results depended on the kind of the quality of the LLM versus, the details of the evolutionary algorithm?
Yeah, that's a great question. So in the paper, we have an ablation where we test different LLMs. And what we noticed is that we get good results as long as the LLMs have been trained enough on code, right? So it doesn't matter, like we had tried it on 2 or 3 like LLMs that are well trained on code, and we got similar results essentially. Now, these LLMs are not able in any way to get these results in one go, right? So you can see here, for example, in this ablation, so this without evolution is essentially the score that you would be getting without an evolution. So just by sampling once from the LLM, right? So the red curve here. Yeah, I mean, it's really a mix of both. But what we saw is that if you have a really bad LLM, then it's essentially like what you'll get is random mutations, so you're not going to get anywhere. But from a certain point, it doesn't really help essentially to improve the size of the LLM and so on, because at the end of the day, the LLM doesn't have much knowledge about this cap set problem, for example. It just, it's just good at coding and trying to detect essentially what the sort of problem, what the sort of combinatorial problem is, but it doesn't have very deep knowledge about what the cap set problem is.
That's very interesting. Actually, there was one other related question on this slide. So you say the skeleton, was the skeleton kind of like an initial solution to the problem?
It is more of a structure. So, so in the case, for example, of the cap set problem, we would tell it, okay, to find a scoring function, a function that essentially tries to score all the nodes, right? And then pick the best one. So this logic of essentially taking the best one, and then that's already, already encoded. The scoring function is the thing that we let the LLM do, right? So if we just give the LLM an empty sheet and ask it to solve this problem, it will be really bad, right? So there is some human element that is really needed at the beginning here. Yeah.
So it's a slightly constrained search.
Exactly, exactly. Yeah.
Thank you.
Yeah, here. I have a question. So, as you previously mentioned during the slides, thank you for the presentation, by the way. As you mentioned, data can be really challenging in this application since it's not like the traditional available data that we can see in different applications. So I just wanted to ask you, what do you think, like what's your vision on how to, or can we actually collect data in this field just to be able to use the other LLM approaches or other pre-training approaches in this application, like in the upcoming time?
Okay, so the LLMs we used here are pre-trained LLMs, right? So we don't fine-tune it, like we use, like coding, think about, like using Gemini or ChatGPT and so on, right? So we're not changing that in any way. Now, the data that we need is essentially the distribution that you want to optimize this thing on. So that essentially, for the bin packing problem, it would be how many bins, what are the incoming items, this kind of stuff, right? So we're not talking about, like data, like LLM data here at all. We're talking about like the distribution of problems that you care about, right? Now, these problems, like naturally, you have this data from the domain that you have. So for example, in the case of say, for example, job scheduling, which is, like corresponding to this bin packing problem, you have a data center that runs jobs already, right? And you have exactly how many servers do you have, how many, like where the machines were put on, the load essentially of each machine and so on. This is the data. So what you need to do in order to get this data is just to store it, right? So you do have already this data, you should have this data, and then you use this data in order to tailor algorithms to this particular, so you use this data in order to find algorithms that are particularly suited for this data, right? So I don't know if that answers your question. I'm not sure I understood it. So does that answer your question? Okay.
To create better mathematical, to solve better mathematical problems for us.
Yeah.
We would probably need data for that. Like we can, as of now, ask an LLM to solve some question or optimize a problem for us, but it would probably give us a poor solution. So because it needs more to learn more in this field. So we don't have data, so we have to do alternative ways into solving these problems now. But in the future, like as we go, would there be like enough? Maybe how would we get good quality data to be able to have smarter LLMs in this particular application, I would say.
Do you want me?
Yeah.
Do you want me to just clarify? I think the question is, why the LLM can't solve optimization problem in zero shot, and will it ever learn how to zero shot problems?
I think it's really hard. Like as I was answering Alex here, I think it's the LLM doesn't know much about these mathematical problems. So imagine asking a 10-year-old kid to answer your CAPSET question. They wouldn't even understand, right? So I do think that there is a need for another component other than LLMs in order to do this, to solve these problems. In particular, you need this kind of evaluator, right? So something that kind of like grounds the outputs into something that, you know, like that is more human knowledge. Now, if you combine an LLM with a grounding, then you essentially end up with what I just talked about here, right? So I don't think that we will have this magical system that essentially you ask it and then it will discover something new automatically like that without any grounding, right? So that's my thinking. Yeah.
Hi, Dr. Fawzi. Can you hear me? Okay. First of all, thank you so much for the talk. I had a two-faceted question about the function search paper that you worked on. So as far as I see, there are two phases to that problem. First up is coming up with a new function or a new algorithm. And then there's another thing which is about proving that algorithm, right? So as far as I see, function search is allowing you to come up with new algorithms, and then maybe you can maybe it's very easy to verify the solutions, right? But then proving those algorithms itself is like a creative task, right? So at what point do you use LLMs for that, or do you have some sort of, maybe the evaluator does that, but then evaluator would also have to be very intelligent in a sense, because solutions or proofs can be really creative, right?
Yeah, so that's a great question. The evaluator, let's maybe, you know, like to make it more concrete, your question, let's project this on the maximum independent set problem, right? So we have an evaluator that is known to be correct, that checks whether the sets that these functions output are valid independent sets or no, right? So what you're getting at the end of the day is a function that outputs correct independent sets. Now the question that you're asking, I think, is how do we actually prove that this is the largest independent set? How do we, yeah, I mean, there has, like, the second step is really to really prove the optimality of this. And this is not something we do. So we do not, you know, like we do not in any way claim that the results that we're getting here are optimal, but we do claim that they are correct in the sense that, you know, like it satisfies the constraints, right? That's a very interesting question of how you combine this with, you know, like provers in order to essentially prove that what you're getting is really optimal. And that's, I think, definitely a next step, yeah.
Yeah, actually, that was the same question, so I think I can give the mic.
So how do you ensure that this scoring function is smooth? How do you design your unit test to make sure that you have a smooth landscape?
So in terms of smooth, what do you mean by smooth?
Yeah, as in the landscape of functions that you're navigating is smooth. So it's not obvious if you were to choose like random unit tests that you're gonna get a smooth score landscape, right?
So actually we don't have a smooth landscape. Like the the landscape I was showing here is just for pictorial reasons, but we do not, like, it's a very discrete landscape, but it's a gradual one, right? So there is a difference between a smooth, where, you know, smooth feels like you can compute a gradient. Here we cannot compute a gradient. Like, think of, essentially you have a program and you want to compute the gradient of a program. It's just, it's really hard, right? So you have a discrete space, but you can essentially evaluate the program to tell you how far or like how good you are, right? So I think it's related to the earlier question here. Like, if you apply this on unit tests, then the way I would do this is essentially by having many unit tests and scoring how many unit tests does this function pass versus fail, and this gives you a score, like 7/10, 8/10, and so on. And then you can hill climb in this way.
Yeah, so I understand that interpretability might be better, but in terms of the quality of the solutions, is this actually better than the RL approach where you pick the next best node? Like in high dimensions?
Okay, so that's a separate question. Okay. Okay, sounds good.